But not everyone who's sitting here is probably going to find that they're able to absorb all of that. And I'm going to walk through a bunch of different ways in today's lecture that dimensional analysis can help you model, okay? For some people, this will all be basically new, and you may only understand the first of them. Some people who have encountered this before may find yourself appreciating all of these different features. But what I'm talking about here is really deep, and every time I come to it, I find myself sort of appreciating with new depth sort of some of the points to learn from here. It's one of these subjects that just keeps on giving, no matter how much you seem to fully understand it. There's new twists to it and remarkable things you can accomplish with. And unfortunately, it's one of those arts which is not widely talked about these days, at least in a lot of academia, a lot of computational and quantitative sciences. So the first benefit is preventing mistakes, and we're going to see that dimensional analysis used by anyone in this room can be one of the most valuable tools for avoiding silly mistakes. Preventing yourself from making a silly error when putting together a model. Putting in the times instead of the division. Adding a stock to a flow. Using the wrong term, the wrong variable in a model. And it turns out that there's a technique, dimensional homogeneity testing, that can be automated. And in fact, in Vensim, it is automated. And I'll show you how to use that. Okay. It can be also done manually. And for an AnyLogic model, you could run through and just make sure that your equations make sense. This is really powerful. Because at first glance, the equation may look decent. But when you really think it through, it may be nonsensical. And you can spot that and eliminate it from your model. So that's really important. It's used by me on a regular basis. It's used by people worldwide. But it's sort of the most simple application of what we'll be talking about today. We might talk about some of it on Tuesday, too, the extension of this lecture. A second thing that's deeper yet is thinking through what parameters need to be used in a formula and how they should be used in a formula. Thinking through that ahead of time. And you can often derive things without doing any experiments or anything. What must be the characteristic behavior of this model? That's really deep. And it's been used historically for real breakthroughs in understanding. So just from base principles, from calculations based on the nature of the dimensions involved. For example, it was figured out what the speed of spread from an atomic bomb explosion must be, without needing to do an actual experiment, and that's important. You can figure these things out. Turns out there's some things with the sort of models we build that can be figured out in this way, and that's useful. That can make you a virtuoso in terms of modeling. Another thing that's I think would speak to the needs of many people in this room and could be applied, although it requires more sophistication than the first in this list, is reducing the number of parameters that are required for calibration and parameterization. One of the problems we saw with parameterization, excuse me, this is a mistake. This should say, it should not say parameterization. It should say calibration. Okay, sorry about that. Calibration and sensitivity analysis. I don't know what I was thinking. There we go. Okay, can you folks still see my slides there remotely? Ooh. Yes, okay, good. So one of the problems that we have with calibration that we talked about last time is that it's the number of parameters that you're calibrating goes up it takes a longer time to calibrate because you have to explore a larger dimensional space. And it can require, you can end up with more situations of kind of where you're unclear how to interpret it. Maybe that multiple parameter values give you equally good results. It takes a lot longer to explore a 3-dimensional space than a 2-dimensional, or 5 than a 4. So keeping down the number of parameters you have to calibrate can be pretty important. And similarly for sensitivity analysis, you can examine the sensitivity of your model with respect to 100 different parameters in turn, but if you start to think about examining with respect to combinations of them, and it becomes extremely burdensome. And even just doing those first 100 or whatever can be really burdensome. We can cut down the number of parameters we need to do sensitivity with respect to. Go from 6 to 4, for example, using dimensional analysis. That's useful. The fourth thing is what I mentioned earlier, creating models with smaller populations that can be used to understand the behavior of models with larger populations. Models with small populations, reduced scale models, are in some sense representative of larger models. Okay? And then finally, there's this phenomenon called power law scaling, where we note the scaling of, when we collect data, we may note that one parameter's value tends to be described very closely by the power law of another. So we may have some variable y that's a function of another variable x, like doing x to the a. And these things are very common. Does anyone remember where we saw that earlier in class? A power law relationship? I'll give you a hint. What does that look like on a log-log graph? We take the log of y. What is the log of y? Speak, use. If I take the log of the left side, what's the log of the right side? Log of y equals, if we have y equals x to the a power, we take log of y, what's on the right side?
A log x.
A log x. So if we plot this out on a graph where we have log x on the x-axis, a log-log graph, and log y on the y-axis, what do we get? Let's suppose that a is negative, as it often is. What do we get? We get a
Linear?
Yeah, it's linear. So we get a line in log-log space. We actually saw that one place. This x was the number of sexual partners over a year, and y was the probability of having at least that number of sexual partners. The log-log graph. Power law behavior. Now, this sort of power law behavior is quite common in complex systems, but it very often results from dimensional considerations. And we can explain it often by recourse to dimensional analysis, the nature of the dimensions involved. Okay, so I'd like to talk about dimensions. And